Okay, so this introductory video is going to give us a basic idea on the asymptotes that we have, alright, and how rational functions behave around these asymptotes. So we have three types of asymptotes, which are the vertical asymptote, the horizontal asymptote, and the slant asymptote, which can also be called the oblique asymptote. Yeah, these three. So first of all, how do we find these three? These three asymptotes can be found as follows. For example, imagine you have a function that says f of x is equal to x plus 1 over x minus 1. Let's start with the simplest among these three, which is the vertical asymptote. Vertical asymptote is simply found by setting your denominator equal to 0. So in this case, we're going to say x minus 1 is equal to 0, therefore x is equal to 1. Meaning, on our x or y plane, the vertical line that is going to pass at the point 1, where x is equal to 1, is going to be your vertical asymptote. This vertical line here is your vertical asymptote. So we can also be given another function that says f of x is equal to maybe 2 over x squared plus 2x minus 3, like that. So again, you get your denominator, so it's going to be x squared plus 2x minus 3. And then set it equal to 0. Alright, so it's going to be what? You're going to have something that says finding the product here would be negative 3, finding the sum here would be 2. And the factors should be 1 and 3, where this guy here is negative. Yeah? So it's going to be x squared minus x plus 3x minus 3. So it's going to be x, open bracket, x minus 1, close, plus 3 x minus 1, like that. Yeah, so meaning you're going to have something that says what? You're going to have something that says let me just rub this up there. You're going to have something that says x plus 3 and then x minus 3, minus 1. So x will be equal to negative 3 and x will be equal to positive 1. So these two are your vertical asymptotes. So if you have your graph like that, you're going to have negative 3 there, and then you're going to have positive 1, and you're going to have two vertical lines passing at these two regions like that and like that. So these are your vertical asymptotes. Vertical lines passing at those points that you found for x. Yeah, so that's how you find your vertical asymptote. Set the denominator equal to 0 in any given function. What else? In a case where you have something like this, so f of x is equal to, maybe you have x plus 1 on top and then x squared plus 4. What are you going to have here? Setting your denominator equal to 0, we're going to have x squared plus 4 is equal to 0, so it's going to be x squared is equal to negative 4. Now, knowing that you can't find, there is no real solution that will come out of here, they're going to have what? S will be equal to 2i. Now, this 2i is imaginary, and on our x or y plane, we don't accommodate imaginary numbers. Therefore, this one here, you can't find the solution for x, simply means, if you can't find a real solution of x, simply means that you do not have a vertical asymptote. So here there is no vertical asymptote whatsoever. Yeah. So we can move to the next one that says horizontal asymptote. How do you find your horizontal asymptote? Horizontal asymptote is found by observing the behavior of your x powers. Alright? Observing the behavior of x powers. For example, if you have f of x is equal to 3 over x plus 1. And then a second one, you have f of x is equal to 2x plus 1 over x minus 4. And then you have the last one that says f of x is equal to 2x squared minus 5 over, we're just going to say x minus 2, like that. Now, what is the vertical asymptote in each of these expressions? Now here, you're going to check your x, your highest power of x on the top and on the bottom. So in our first example here, the highest power of x that we have on the top is 0, right? Then the highest power of x that we have at the bottom is 1. Now notice that 0 over 1, 0 is less than 1, alright? 0 is less than 1. Therefore, this function over here is tamed to be a proper rational function. This one is a proper rational function. The idea of proper rational function comes in from the fact that if you have 1 over 2, right? This is a proper fraction. If you have 3 over 5, this is a proper what? Fraction. So the proper rational function comes about when your highest power of the top of your x on the top is less than your highest power of your x at the bottom. So this is a proper rational function. And the horizontal asymptote for a proper rational function is always y is equal to 0. And if you have your x or y plane like this, y equal to 0 is simply the x-axis there, where y is equal to what? 0, the x-axis. So you're going to have your x or y plane like that, and then you're going to have a line that passes right there, and this line is going to be your y is equal to what? 0. Yeah. So that is your horizontal asymptote. So here the behavior of the horizontal asymptote that we're following is simply the fact that the highest power of x on top is less than the highest power of x at the bottom. So we'll talk more about this. Let's move to the next one. Next one here, we're going to see that the highest power of x on top is equal to the highest power of x at the bottom. Alright, so in such a case, you're going to get the coefficients of the highest power of x both at the top and at the bottom. So here the coefficient is 2. Let me change my color. Here your coefficient is 2. Here your coefficient is 1. 2 over 1 is simply 2. Therefore, your horizontal asymptote is y is equal to 2. Cool. Let's move to the next one. Last one is saying your highest power of x at the top is 2. Your highest power of x at the bottom is 1. Now, 2 over 1 is an improper function. Alright, 2 over 1 is an improper fraction. Sorry, an improper fraction. So in such a case where you have an improper like that, you no longer have a horizontal asymptote. So here there is no horizontal asymptote. Okay? Instead, you're going to have an oblique asymptote. So we'll look at that later on. But let's focus on the horizontal asymptote. So horizontal asymptote only comes about in these two cases, 1 and 2. Okay? So let's look at more examples of these. So let's say you have f of x, which is equal to what? Let's say my f of x is equal to something like, what can I have? Let me have a 2x plus 1 over x squared minus 2x plus 3 like this. Now I'm looking for my horizontal asymptote. What am I going to see? I'm going to look at my highest power of x on the top. So here, it's more like I have two x's, but this second x here is sort of like a x to the power 0, okay? So I have x to the power 0 and then I have a x to the power 1. So which one is greater? Of course, x to the power 1. So on the top here, I have my 1 over. On the bottom here, I sort of have three x's, 1, 2, and my x to the power 0. But the highest power is the one that says 2. So I sort of have a 1 over 2. So we said this is going to be a proper function. A proper function. So therefore, my horizontal asymptote is going to be the line y is equal to 0. Yeah. I can have anything. The only basis where you have y is equal to 0 is having the fact that your highest power on top is greater than your highest power at the bottom. For example, let's say I have, I also add a plus x to the power 5, right? And then down here I add a plus x to the power 7. So in this case it changes where my highest power on top is 5. My highest power at the bottom is 7. 5 is less than 7. Therefore, my horizontal asymptote is still y is equal to 0. Always. Yeah. And then the next example is if they are equal. Yeah. So let's have x power 3 plus 1 over x power 2 minus 3x power 3 plus 4. So my highest power of x on top is 3. My highest power of x at the bottom is still 3. Right? So after I see that, I'm going to focus on their coefficients. What is the coefficient of the x3 on top? 1. What is the coefficient of the x3 at the bottom? Minus 3. So my horizontal asymptote is going to be y is equal to 1 over negative 3 like that. Yeah? That is how it always goes. So this is the only time when I can have my horizontal asymptote. But in a case where the power at the top is greater than the power at the bottom. So if I have my f of x is equal to something like 2x squared plus 1 over x squared minus 3. Oh, sorry, not x squared. Let's just say x minus 3 like that. So I can see that my highest power at the top is 2, my highest power at the bottom is 1. So in this case, I'm going to have a oblique asymptote, an oblique asymptote. Now, how do I find my oblique asymptote? I'm going to use long division. So how was my thinking? I have forgotten it. Should have kept it in mind. Alright, so I'll just say x minus 3 root of 2x. I have forgotten what I wrote, so I'll just write whatever comes to my mind. 2x, let's say, let me just say this. The function is 2x power 3, let's say plus 4, yeah, and then x minus 1. Let's just keep it as simple as that. So we're going to see that the power on the top is greater than the highest power at the bottom. So I'm going to employ in long division, where I'm going to say x minus 1, yeah, x minus 1, and then I'm going to do a comma 2x power 3. Now my x's should always be in proper descending powers. So here I must have a 0x power 2, and then I must have a 0x for me to have a plus 4 like that. Yeah. So I'm going to start using long division in this sense. Let me just rub the top here. I'm going to start using long division in this sense. X into 2x cubed. It's going to give me what? It's going to give me x into 2x cubed is going to give me a 2x squared. 2x squared by x is simply 2x cubed. 2x squared by negative 1 is simply negative 2x squared, like that. Alright, so I'm going to subtract. There I'm going to get a 0, it cancels out. Here I'm going to get a positive 2x squared. I bring down the plus 0x like that, and then I'm going to say x again into 2x squared. That's going to give me a plus 2x, yeah. 2x by x is going to give me 2x squared. 2x by 1 is going to give me negative 2x, like that. Subtracting this will give me what? It was going to give me a positive 2x, because these guys will cancel here. It's going to be a positive 2x. Now here I'm going to see that my 4 drops down, so dropping down is going to come a plus 4 there. X into 2x is simply plus 2. 2 times x is going to give me 2x. 2 times negative 1 is going to give me negative 2, like that. Subtracting this will give me what? This will go 0. This is going to give me a 6. Yeah. So I have noticed that after dividing this, I'm going to have the quotient of this on top here, and then the remainder of 6. Quotient of 2x squared plus 2x plus 3, and the remainder of 6. Yeah, so let me write that properly. So it's going to be 2x squared minus plus 2x plus 2, something like that. And then what else? Yeah, so this was my quotient that was on top. So this is going to be my oblique asymptote. My y is equal to this. Now I notice that this is a quadratic. So how do I graph up my quadratic? If I do something like that, my quadratic will come out like that, right? Now this quadratic of mine is my horizontal asymptote. When I say that, let's say I had a vertical asymptote of something like this, meaning my graph would come from there, and it would also be like that, or it would come from there and also go like that, whichever way. Yeah. So the last behavior that we would see that these rational functions have with the asymptotes is that they always run parallel. For example, you have something like this. So this is your horizontal asymptote, this is your vertical asymptote. They always run parallel in this sense. Somewhere about here they'll be far away, but as they start going this side, they will sort of like go towards your asymptote. They will go towards your asymptote until infinity. Never touch, never cross. And then the second behavior is that they always run in diagonal basis. Alright? So if you have your first function going there, meaning your other one should come from there. If one is starting from there, meaning the other one should go like that. You can never have two like this and like that. Never. You can never have two like this and like that. Never. They always run diagonal. So let's say maybe you had two vertical asymptotes. Let's add another one there. Meaning your graph can either come out like this. So if your graph comes out like this, notice that diagonal you'd consider there and there. Okay? Or if your graph came out there, diagonal you'd there and there. You can never have like this and like that. You can never have like that. You can never have this and that and that. Never. Alright, so it's always in diagonal. So this one will be here and this one will be there. Yeah.